last couple of weeks are scheduled. So we have 212 meets today, 300 meets tomorrow, both exams on Friday. And then 212 project next Friday, and then 212 final that 10.
Yep.
So that Monday.
Yep.
And then are we gonna have any more 300 homeworks after Wednesday?
So I wanted to put something out there, but I'm not going to make it required. It will either be optional, like if you submit it, you get extra credit, or if you submit it, I'll drop the lowest homework or something of the sort. And that will, I think, hopefully help people with the level of busy that we have at the end of the quarter. So I did think about that over the weekend, and that was the conclusion that I came to. I don't know exactly what I want to do with it yet, but I'll make something available, but on an as needed basis.
What's our last day on Friday?
Or what, sorry,
Last day?
last day for is. Oh, yeah, no final in 300.
So.
Yeah, the very last exam for this class will be this Friday.
Friday, and then finals will be that Monday,
There's a lot happening in our next couple of weeks.
And then our most project.
That's the last day of class, a week from Friday. Yep.
What are you covering next week then? 300?
300, I'm hoping to, if there's any last bit of graphs, I'll probably cover that for a day or so, but after that, I want to talk a little bit about interviewing, getting things like internships and jobs in computer science, as well as just applying everything that we've done in an interview setting. So we might have some practice interview problems and some time to work on those. That's what I think would be the best use of the final week, since we've covered the content at a pretty reasonable rate. We're already, I think, after trees, we finished what this course is supposed to cover according to the generic course description. And so I've been working to try to make I've heard that the transition to algorithms is really rough. So I'm trying to make the transition to algorithms a little bit less rough. And then also want to focus on, now that you're through data structures, assuming you know and remember all of this content, you have enough in your brain to be useful and valuable to a company and to start making a paycheck from them at an internship level. So I want to talk about how to transition from this point in your academic career and start working on opening some doors in this career. It's not what everybody's in this class for, but I'm hoping it's what most people are in the class for, so it would be useful to most people. And if not, then it's just good practice. So last time we talked, we were transitioning and talking about how trees are viewed as graphs. Trees are a subtype of graph. And then we talked about, let's just launch and talk. We talked about rooted trees and how we can root a graph that is acyclic and undirected and connected. All three of those things mean you have a tree. And then you can root that tree at different places and you get a unique tree structure out of that. Note, this isn't a binary tree or a binary search tree. You just get a tree structure if you root a tree. A graph that adheres to that is a tree, you root it, and then you get a unique tree out of it. So were there any questions on this before we move on to new stuff? So here we see how rooting the tree at A creates a unique tree, rooting the tree at F creates a unique tree, and that creates the directionality. We take an undirected graph, we root it, and suddenly we have a directionality flowing away from that node. Let's talk a bit about a concept of density. So we refer to, when we talk about the number of edges in the graph, that is what we refer to by density. You can imagine a very sparse graph that has some vertices and very few connections between those vertices. We call it a dense graph if we have lots of connections between those vertices. So let's first talk about let's define the concept of dense. So if the cardinality of the set of edges is in theta of the vertices squared, then we define the graph as dense. So what that means is it's not proportional to the linear number of, or linearly proportional to the number of vertices, it's quadratically proportional to the number of vertices. And we talked about, as we drew up a couple of graphs last time, that as we got denser and denser, then we found that if we had the most edges possible in a graph, we ended up with something that was quadratic. So the question is just now, if we look at some number of edges and we were to derive a formula for how that scales based on the graph size in terms of the number of vertices, if that scales proportional to the square in any formula that is based on that square, then we would call that graph dense. So that is the formal definition. The unofficial definition is the graph has lots of edges. We will define sparsity in terms of that cardinality of the set of edges being in big O of the number of vertices, size of the number of vertices. So if it's linear or less than linear, note that it could be some constant times linear, then we call the graph sparse. And unofficially, you can think of this as something like most possible edges are missing. Questions on our definitions of sparse or dense?
When you say most possible edges, that just means like how many theoretically.
Yeah, if the graph were complete and that every possible edge existed and you removed most of those edges, you would end up with something that's likely big O of B, number of vertices. So now we need to figure out, okay, we have this concept of a graph, but how do we convert this generic idea into code representation? And it turns out that we have some options when we do this. So the first we're going to call an adjacency matrix, and the second we're going to call an adjacency list. So we're going to go over each of these in significantly more detail so that you know how to store the concept of a graph, because we don't frequently store them in terms of the actual nodes, node objects, and edge objects. We can, and that might make sense for some applications, but frequently we want to actually abstract away from that concept of storing them as objects, and instead store them in some other fashion. So an adjacency matrix is just a 2D array of booleans. Number of vertices, find the number of vertices, 2D array of booleans. Before I talk about anything else, why does this make sense? What does that represent? Anyone have any intuition, ideas?
It's supposed to be like storing a 2D, what was it? 2D matrix kind of row major order or something?
Yeah, what do the cells represent? Each cell can either be true or false. What do you think they represent?
Oh, truth table.
Truth table? That's a good guess.
I think there would be whether the vertices are connected.
Yeah. So we're going to have a connection from the row vertex to the column vertex, and that will be true if an edge exists between those vertices, and false if an edge does not exist between those vertices. So we have a from the row to the column interpretation. So as an example, we have this graph. So you can see that we have the from in the row and the to in the column. So is there an edge from A to A? That is what this very first cell represents, and that is false because there is no edge from A to A. On the other hand, there is one from A to B. There is one from C to B, but not one from B to C, since this is directed. If this was undirected, then you wouldn't need to store this entire table. If it's undirected, you can actually get away with a jagged array that only goes up to and includes the diagonals. You wouldn't need either this portion or this portion because it would be symmetrical. So you can save yourself some memory if it is undirected, but in general, this is all you store. You don't store anything that represents this visual outside of this data. So now we know there are 4 vertices, and we know the associated connections. Because nothing about this really matters where these are located proportionally to each other. Note that this is only for edges that don't have weights. If these edges did have weights, what would you do about that? How could we fix that problem? So maybe A to B has a cost of 5, C to B has a cost of 7, C to D has a cost of 12. How could we change up this representation to include that information? Yeah.
Just change the true false to these.
Yeah, if we instead of storing booleans, stored integers. If there was a value greater than or equal to 0, then that would give you the connection, the weight of the connection. How would you represent a lack of an edge? You can't have false there.
Just, is there?
Usually we put -1 if we don't allow negative weights in the graph. But now as soon as we do allow negative weights in the graph, we need to come up with some special representation of a way of saying this edge doesn't exist. And that could be done with the integer type and null, or some other special way of handling that. But yeah, that's exactly what we do. Booleans, if there are no weights, integers if there are. Yeah.
You kind of talk about, so is it, if it's, I'm kind of confused on the, between A and B and then in the graph A and B. Like, is the arrow saying from A to B when it's that first true kind of?
Yeah, so this edge is from A to B. So this is the from, and this is the to. So the A to B is right here. From A to B. Which is why we have a C to B. From C to B is from C to B. And the opposite of that, from B to C is false, because there is no edge with that direction out. Can I fully answer the question? Find my eraser for it, but that's under out recorded. Okay. People feel like they understand the concept of an adjacency matrix? Because now we want to go and analyze how it is going to perform. Because we said there are 2 different types, so if we want to be able to know when to use an adjacency matrix and when to use an adjacency list, there are pros and cons to each. There are times where you would prefer to store a graph in an adjacency matrix, and times you would prefer to store an adjacency matrix in an adjacency list. So let's first ask, how long does it take to get a vertex's out edges? So now my question is, for C, what are the out edges of C? So it's gonna be some kind of list. It'll be a list of nodes that are the connections, the neighbors of C. So B and D, yeah. The list would contain two vertices, B and D. So now the question is, if you had to write a program to do this, how long would it take that program to run proportionally to the number of vertices in the graph? Is it constant? Is it linear? Is it logarithmic? Is it quadratic? Exponential?
What's the program we use on this chart?
It's going to determine the out edges of a particular query. So if I gave this subroutine C, it would return the list BD. If I gave it B, it would return the list A.
It's gonna read. So it's.
Yeah. Yeah, that's exactly right. We need to look at this existing structure. The graph structure already exists, and we need to query for this row, what are the truths? So false, don't add A, true, add B, false, don't add C, true, add D. Return that list. And this will grow proportional to the number of columns that we have. The number of columns we have is the number of vertices in the graph. So that tells us that this is going to be big O of the number of vertices. The next question, I guess, does anyone have any questions about why that's linear proportional to the number of vertices? How about a vertex's end edges? So if we go back, now we care about, okay, what is the list of edges coming into B? So A and C would be the right answer. How do we get that? Yeah, that's exactly right. You're gonna look at the columns. So to get the edges that are coming into B, we're going to return A and C, those rows that are true for a particular column. How long is that gonna take? It's just linear again, because the number of rows is gonna be proportional to the number of vertices in the graph. How long does it take to decide if a particular edge exists? Now I want to ask, is there an edge between D and B?
And edge or edge, or either.
From D to B?
Constant.
Constant, yeah. So to look this up, we just need to be able to say, row D, column B, is this true or false? There's nothing about this that requires an iteration or a recursion. We just go look up a particular cell. And since we know these are all mathematically offset, they're just multiplications and additions, it's gonna be constant regardless of where in this structure your query is. Does that make sense? So that's constant. How about inserting an edge? We want to modify the graph now to make an edge between D and B. How long is that gonna take? Constant again, yeah. We're just gonna go to a particular place, we're gonna do a find for it, and then we're going to swap a false to true. And that makes an edge between those vertices, so it is also constant. Deleting an edge, how long does it take to take an edge that exists and remove it? That is also constant. We're going to go find something that is true at a particular query, the edge exists, and we're going to swap the true to a false. How much memory do we need? To store an adjacency matrix, we need some amount of memory. How much memory is that proportional to the number of vertices in the graph?
B squared.
Yeah, it's b squared. So we know that there are v rows and v columns. So v times v total cells. It's b squared. Now I have a question for you. Is this better for sparse or dense graphs? When do you think this is a more efficient structure?
It's something that'll always be impacted by how big it is, or?
It will be, but I think any representation we would have would be. The answer is basically it doesn't matter. We get these results regardless of the size. It turns out that in order to know whether it's better for sparse or dense graphs, we have to be able to compare it to an adjacency list. So I'm going to put this question on hold for just a second, but think as we go over the list, comparing this to an adjacency matrix, which one is this better for sparse or dense graphs compared to an adjacency list? It'll turn out that a list will have a benefit and the matrix will have the opposite benefit because it makes up for some deficiencies in the adjacency list. All right, so an adjacency list, now instead of a matrix of cells, it is going to be an array of linked lists, kind of like a linked hash table. Each linked list likely has a dummy head and then points to all of the connections of the B sub ith vertex. So if a list is empty, it basically means that there are no outgoing connections from that vertex. So that vertex has no neighbors. Question I have, what is the most number of elements that can be stored in this list?
B minus one.
If we could have a self edge, if we could have an edge from a vertex to itself, you're basically right. But the answer is B. Just like in the adjacency matrix, for a particular row, everything could be true. And we have as many columns as we did rows. So because of that, we could have up to B elements in this linked list. So if we have an understanding of the adjacency matrix and the adjacency list, here I have a graph for you with nodes that are numbers 1, 2, 3, 4, and 5. Go ahead and draw out an adjacency matrix and the adjacency list, I should say and list. Draw the adjacency matrix and list for the following graph. So for one, we're going to have a V by V array of booleans. And for one, we're going to have a list of V linked lists. Array of V linked lists. All right, we want true or false in each of these cells. In row 1, where do the trues go? 2 and 5. We have true and true, false, false, false. In row 2, where do the trues go? We have 2 going to 1, 2 going to 3, 4, and 5. So just not itself. So true, false, true, true, true. For 3, between 2 and 4. So true and true, false, false, false. 4 goes to 2, 3, and 5. 3 and 5. And 5 goes to 1, 2, and 4. That is the adjacency matrix. So now we want the adjacency list. So that's going to look like an array of linked lists. So I like to draw these vertically as well. So we're going to basically have the 1, 2, 3, 4, and 5 list. They start out being null. And we said that 1, we have 2 and 5. So we're going to have a pointer to a linked list that says 2, that points to another node that says 5. And that is the list for 1. 2, we said 1, 3, 4, and 5. So we're going to make 1, 3, 4, and 5. So it basically looks like this. I don't know if I want to go through and draw the whole thing. For 3, we would have nodes for 2 and 4. For 4, we would have nodes for 2, 3, and 5. 5, we would have nodes for 1, 2, and 4. Does the list concept make sense with this? So if this is null, then there are no elements there are no neighbors to that node. And then at most, how many elements can be stored in one of the lists? V. If each one of these were true, then there would be V nodes in the linked list. 2 is really close to that. It's only missing an edge to itself. So if it did have an edge to itself, then there would be 5 elements or 5 vertices.
What would it look like if it had an edge to itself?
In this case, we would just have something like. What? Yeah, self edge or a loop. And since this is undirected, it would be undirected. And then this would be true.
What's like the most practical case of C?
For a self loop, there are tons. If you have any way to get from something to itself, so. Let's say we have some kind of Markov decision process. The Markov decision process is a probabilistic loop from one node to another node. So you basically flip a coin or use some kind of random number generator to decide where to go. You could end up right back where you belong. Or right back where you started as part of that. You could be in a losing state and stay in a losing state. You could move from a losing state to a winning state based on some action that you take. So there are lots of different graph ways you can use a graph or things that it can model, and anytime that you can make some kind of action and end up back in the same position, you would have a self edge in the representative graph. So rather than draw the rest of this out, I actually have images that I can show you on the slide. I just wanted to go through the logic of how to construct it. So this uses 1s and 0s instead of trues and falses. That's perfectly fine. Anything that you can use to represent binary is perfectly fine here. And you can see that the adjacency list is just a list of linked lists. So a 2D structure. Array of linked lists. Let's go through the same process that we did for the adjacency matrix for the adjacency list. Let's take a look at those same questions and their associated runtimes, assuming we have an adjacency list. So how long did it take to get a particular vertex's out edges? It isn't quite as straightforward a question anymore, is it? You may want to split this up now into sparse graphs and dense graphs, based on our previous definitions of sparse graphs and dense graphs. If it's a dense graph, what did we say was the definition of a dense graph? A lot of edges. So if most of the edges are true in this, how long would it take to get a vertex's out edges? How long would that list be if most of them are true? Be proportional to the size of the list, or proportional to the number of vertices. So big O of B. If it's sparse. What do we think on average would be the average length? If it's in the total number of edges is in big O of B. What does that mean in terms of the adjacency list? It means that for each vertex, there are a constant number of edges. That's how you get big O of V. And since there are V nodes, the number of edges for each one of those nodes can't be big O of V, because then we'd have V times V. So to get big O of V in the entire structure, we need something that is constant on a vertex by vertex basis. If each vertex has an average of one edge, then we would have something like an average of a constant number of nodes in any one given vertex. So we split this up now and say, to get the out edges, it's big O of V for dense graphs, but big O of 1 for sparse graphs. What was this for the adjacency matrix? It was linear. So with an adjacency list, if we have a sparse graph, we can improve on the adjacency matrix runtime for getting the vertex's out edges. How about a vertex's in edges?
Be similar to out edges like it was for matrices.
It would be if we could, in constant time, figure out where it was going to be in the associated edge. So if we look back at this particular list, if we want to get the in edges for 5, we need to query, does 5 show up somewhere in this list for 1? How long does that take to figure out? It depends on if it's a sparse graph or a dense graph. If it's the dense graph, and this may have up to B elements in it, in which case it's going to take big O of B to figure out just whether 5 is an in edge to 1. And we have to ask the same question of 2, or the same question of 3. Or if it does not, if there are no in edges for 5, then to figure that out, we need to query each entire list to figure out 5 does not appear anywhere in any of these lists. So this is a harder problem than the out edges, because we don't just have easy access to columns like we do in the adjacency matrix. So because of that, we actually get significantly worse relative for this. If it's a dense graph, then we're going to need v squared. Because we're gonna need to look at every single list and try to identify, is a particular vertex in that vertex's list of out edges. Which means that it's in the in edge, it's an in edge for the other. Which is gross. This is for directed graphs. If it's undirected, then we can just query the out edges again, because we know that there's an in edge for every out edge. So if it's undirected, it's actually b and 1, but if it's directed, it's b squared and b. So, sorry, I should probably make that clearer. This is for directed. And undirected looks like this. I guess. For the vertex in edges, it's this or that. So lots of considerations already. How about to decide if an edge exists? It would be for sparse graphs. If we know that there's an average of, that's a very good point. It's O of 1 if it's a sparse graph. And there's a total of some proportion of just the number of vertices edges. Which means that we would have something that looks kind of like this. Which means that it would be basically a constant time lookup to see, all right, is there an edge between 3 and 2? Well, there's an average of 1 edge. So on average, we're gonna be looking one place. Great, it either exists or it doesn't. But now if we have a dense graph, where we're proportional to the number of vertices for each one of these, how long is that going to take? We go with B. Because it's gonna be a long list like this, to be able to figure out if a particular edge exists, we don't know where in this list it is. If we're querying, is there an edge between 2 and 1, that's a fast answer. If we're querying, is there an edge between 2 and 4, that's a slow answer. On average, it's gonna be somewhere between fast and slow, it's gonna be about slow over 2. Which is proportional again to the length of the list, the number of vertices in the graph. If there are 10,000 vertices, this is gonna be a long lookup. Having a 5 by 5 doesn't really show how slow this can get. If there are 10,000 vertices, we expect to look 5,000 positions into this list on average before we find it, which is proportional to the 10,000. So again, we have a difference between dense graphs and sparse graphs. What was this for the adjacency matrix? It's constant. It's constant. So this can be worse. In the best case, it's the same as an adjacency matrix. In the worst case, it's worse. So here we have, in the best case, it's better. In the worst case, it's the same. Here, in the best case, it's the same. In the worst case, it's worse. For directed graphs. And then we get this for, so it can be better or worse, depending on whether it's directed or undirected. And then to decide if an edge exists, then it, in the best case, is the same, and in the worst case is worse again. How about to insert an edge? How long is that going to take? Assuming we insert at the front of the linked list, or we have a tail pointer to insert to the back of the linked list, it's going to be constant. to delete an edge? It can be, depending on if you intelligently have a way to locate that particular edge, if you store that. So it can be constant if you do this the brute force way. It would actually, you have to go find the edge in the list and then delete it, so it also could be linear, depending on if you do it that way. What about the space requirement? How much memory do we need proportional to the number of vertices for an adjacency list?
Would it be the same as adjacency matrix?
It would be for a dense graph. So if we're gonna be making a number of nodes that is proportional to the square of the number of vertices, that means there'd be a number of nodes. We have the vertices times vertices, number of nodes, but what about sparse graphs? It is linear. Because we only need an average of one node per vertex, since it's in big O of B by the definition of sparse. Yeah,
So what's the difference between the vertex being squared inside of the and versus outside? So like for the space requirements,
yeah, no, that's, this square should be outside, sorry, that's my bad. Square should be outside. It actually doesn't really make a difference, vertices squared is the size of the list squared versus the, yeah, that doesn't really make math sense for it to be inside. So it should be outside. You can only query the size of a set, you can't query the size of vertices squared, that doesn't make sense. This is the size of that set squared. All right. So all of this said, are adjacency lists better for sparse or dense graphs? Now that we kind of have the ability to compare them, adjacency lists are much better for sparse graphs. Adjacency matrices, what are they better for? They're actually, compared to an adjacency list, they're better for dense graphs. You're gonna get, on average, better performance if your graph is dense, if you have a constant way of accessing things like an edge existing. And we had big O of B for the vertexes in edges. We have the best case here, we have the best case here. We have and remember that we're looking at dense graphs, so we can only have worse performance for the adjacency list, which makes the adjacency matrix better for dense graphs. We get better overall performance compared to an adjacency list. So it doesn't vary, but it's better than a list for most things for a dense graph. Questions on representing graphs internally?
We use the absolute values here, but can we be a negative number?
This does not represent an absolute value, it represents the size of a set. It's the cardinality of the set of the number of vertices. So replace that with the number of vertices.
Okay.
So if there were 5 vertices, then we would have 5 squared, we would have, yeah, it's the size of a set. Great question. Others? All right, I'm very briefly going to introduce the next topic. We don't have a ton of time to dive into it, but now that we can store a graph internally, it might be useful to be able to answer some questions about our graph and be able to ask the questions, how long does it take to answer these kinds of questions? So one of the most frequent things that we want to do with a graph is search it for some kind of meaning. You can think of the graph as the vertices are the intersections in Spokane, and the edges are the roads between those intersections. Now, one of the searching queries would be, how long does it take for me to get from the catalyst Hey, it's back. So that's basically where we're going to be headed, is we want to be able to ask questions about graphs. So we're going to talk about the questions we can ask and how can we answer them by looking at our internal graph structure. I will see you tomorrow for that.